Lesson 4, Symmetry and Transformations, Mathematical Groupthink. So far in our course, we have discussed rhythm, individual notes and pitch, and combination of notes into scales and chords, and tuning. Now we can explore composing music. We will also uncover evidence of Bach's genius, not just for music, but for mathematics and for puzzles too. This lesson is about two words you know, symmetry and transformation, but now from two vantage points, the mathematical one and the musical one. Symmetry. Let's start with symmetry. What is it? Symmetry refers to a sense of harmonious and beautiful proportion and balance. It is everywhere in our lives. Nearly all laws of science have their origins in symmetries. In biology, starfish are symmetric around a central point. Humans have bilateral symmetry. Our left side looks like our right side, approximately. Nature, everything that grows, exhibits symmetry. Symmetry occurs in all areas of art and architecture, and most arts and crafts. Literature, too, can have a symmetrical structure. Social interactions are judged by their symmetry. Shaking hands is a prime example. The golden rule in either the Jewish or Christian version is based on symmetry. Simply put, it is treat others the way you want to be treated. Music displays symmetry in different ways, from constraints on musical form to the formation of scales and chords, to melody, harmony, counterpoint, and rhythm. Some musical instruments, such as the violin or a timpani, even have physical symmetry. Now, ancient philosophers often considered the study of symmetry to be a form of mathematics. Not surprisingly, mathematics has very precise definitions of symmetry. It uses the language of an advanced topic called group theory, but we can understand it with much simpler analogies using arithmetic, basic geometry, and graphs. There are various types of symmetry, and we'll focus on the ones that appear in music. The first is translation. Now, in simple musical terms, a musical translation is simply a repetition of a rhythm or melody. It's a shift from one time to the next. Think of what the right hand plays in Beethoven's Moonlight Sonata. For mathematical sticklers, this is only approximate symmetry, since the piece eventually ends. True mathematical translation would go on to infinity. Shifting a sequence of repeated notes up or down is another example of translation. Think of Bach's famous Toccata and Fugue in D, BWV 565 for organ. That's a wonderful example. For a mathematical example of translation, think of the positive whole numbers, 1, 2, 3, and so on, and then add 1 to each to get 2, 3, 4, up to infinity. That's translational symmetry, which I think is the least interesting of the types. Reflection. In music, this could be two lines where the lower one is the upside down version of the upper one. Bela Bartok used this in his String Quartet No. 5 and in his music for strings, percussion, and celesta. In geometry, think of two figures that are mirror images of one another. Or think of the positive and negative whole numbers. The negative ones are a reflection around 0 of the positive ones. Incidentally, if you do a reflection and a translation, it's called a glide reflection. In music, play a passage and play it again upside down, but up a note. Chopin used it in the left-hand opening of his waltz in A minor, Opus 34, number 2. Rotation. Now, mathematically, rotation is when an object can be spun around a fixed point without changing the overall shape. A palindrome is a word or phrase that reads the same forwards or backwards, like the word rotor, R-O-T-O-R, or the phrase, Madam, I'm Adam. They are rotationally symmetric around the middle letter. A musical palindrome is what every musician practices ad infinitum, an ascending scale followed by a descending scale. A musical example can be heard in the notes F, E, D, C sharp, which rotate or spin around a D sharp between the two middle notes. Ravel repeated this sequence many times in his Rhapsody Espagnole. Notice that a full scale doesn't achieve rotational symmetry until an octave is reached. And that's because the gaps in the scale are uneven. But if you think of the 12 tones, they have rotational symmetry, the first 6 and the last 6. And then there's scale, the last of the symmetries. That's when an object can be expanded or contracted without changing shape. A famous example is mathematician Benoit Mandelbrot's fractals, which can be seen in nature, as for example, in the patterns in broccoli florets. A musical fractal happens when a theme harmonizes with a slowed down version of itself. Symmetry in music builds up expectations of what comes next, but predictability is boring if there isn't an occasional surprise. Transformations. Now that we have a clearer understanding of symmetry, let's turn our attention to how symmetry is used and how it is achieved in music. The one-word answer is transformations. The mathematical definition of transformation is a process where one expression, such as an equation or a shape, is converted into another according to a mathematical rule. The two versions are equivalent in some important ways, but they are represented differently. A simple example is when you zoom in or zoom out on an image. The image is the same, but it's also different. Mathematics and music have parallel transformations. In both fields, they add beautiful structure. Mathematician and violinist David Kung says, this analogy may account for some of the psychological, maybe even the neurological connections between mathematics and music. The best known musical transformations involve inversion, reflection in time, transposition, and augmentation or diminution. Each provides a way for composers to produce variations in their creations, and each of these can be understood from a mathematical viewpoint. The words sound technical, so let's simplify. Picture a world globe. The north and south poles are endpoints of a vertical axis through the globe around which the world spins. The equator marks horizontal axis. Using these two axes, the world can be divided into hemispheres in two ways, western and eastern, or northern and southern. Time zones change as you move east or west. Latitude changes as you move north or south. This is analogous to something we talked about in our first lesson. Time, or rhythm, is horizontal, while pitch is vertical. World travel can take you from the western to the eastern hemisphere, Canada to China, or from the northern to southern hemisphere, Canada to Argentina, or a combination, China to Argentina. Here is another analogy to help you visualize the key transformations. Hold up a letter size 8.5 by 11 inch piece of paper. Flip it vertically around the horizontal axis, from here upside down. Flip it horizontally around the vertical axis, and the beginning and the end trade places. We're going from here to here. If you flip it both ways in sequence, what happens? It goes from up here to down here. As we shall see, those same operations take place in music. There is one other characteristic to notice that will lay the groundwork for where the mathematics comes in. If you flip it one way and then back again, you undo the transformation and you return to your starting position. Flipping vertically is called inversion. Musically, that would mean playing the music upside down. With numbers, it would be the same as taking the negative of a positive number. So 5 becomes minus 5. In a graph with x and y axes, it would be a reflection over the x-axis or horizontal axis. If you remember your notation for functions in mathematics, that would be a transformation of f of t to minus f of t. That is inversion. Imagine what Twinkle, Twinkle, Little Star would sound like if it were played upside down. In Bach's Invention number 4 in D minor, the first 2 bars, played by the right hand, are in the shape of an uppercase M. In the next 2 bars, that figure is played by the left hand, but inverted, which turns an M into a W. A famous example is Der Spiegel, the mirror duet, with dubious attribution to Mozart, likely not by him. It's known as a table canon because 2 violinists stand on opposite sides of the table. Each plays the music the way each sees it. One is right side up, one is upside down. Now, flipping horizontally is called retrograde or retrogression, or going backwards. Think of that as reflecting in time from future to past. Musically, that would mean playing the music backwards, from the end to the beginning. With numbers, it would be the same as taking the reciprocal, the 1 over of a number. So 5 would become 1/5. In a graph with x and y axes, it would be a reflection over the y-axis. In the language of mathematical functions, it would be a transformation of f of t to f of minus t. And that is the second transformation, retrograde. A canon of this form is called a crab canon. There's a lovely example in Bach's The Musical Offering, BWV 1079. Canon number 1 is formed by playing Frederick the Great's royal theme, which consists of 18 bars, simultaneously forwards and backwards. Now, I'm sure you can figure out what to call the process of doing both, flipping horizontally and vertically to go backwards and upside down. It is called retrograde inversion. There's another way to think of this. It's a rotation of 180 degrees. With numbers, it would be the negative reciprocal of a number. 5 would become minus 1/5. In a graph with x and y axes, it would be a reflection along the diagonal, from the top right quadrant to the bottom left. In the language of mathematical functions again, that would be a transformation of f of t to minus f of minus t. So that is a retrograde inversion. Let's return briefly to the analogy of the globe and expand on it. The Tropic of Cancer and Tropic of Capricorn are parallel to the equator. Transposition would mean traveling along one of the tropics instead of along the equator. So this would still take you around the world in a horizontal direction, but at a latitude higher or lower than the equator. In music, transposition involves moving up or down in pitch. Instead of starting on A, start on D, transposing up an interval of a fourth. Transposition means changing the key. The melody is still easily recognizable, it's just played a little higher. In a graph, it would simply be moving the figure up or down by a fixed amount. It is a vertical translation. With mathematical functions, it would be changing f of x to f of x plus c, some constant number. What if you slow down or speed up your trip so that it takes you twice as long or half as long to get back home? Those transformations are called augmentation or diminution, stretching or shrinking by some factor, such as 2. The augmentation of a melody is twice as slow. The diminution is twice as fast. Did you ever sing rounds like row, row, row your boat? One singer starts, another starts a few bars later, and so on. It could go on forever if enough voices join in. That transformation is called a translation, an idea we saw earlier when we discussed symmetry. Imagine a graph with time on the horizontal axis. Singer 1 starts at time 1 or bar 1. Singer 2 starts at time 5 or bar 5. It's a sideways shift along the graph. In mathematical function language, the function g of t is equal to f of t minus 4. So, where's the mathematics in all of this? It is a subject called group theory, not to be confused with group therapy. The musical techniques we just discussed, inversion, retrograde, and transposition, can all be interpreted as group operations. I took a whole course in this as part of my undergraduate degree in mathematics. I'll just give you a small taste of it here. Multiply a number by -1 and then do it again, or take the reciprocal of a number and then do it again. For each of these, repeating the operation gets you back to the original, which is the same as doing nothing. This is the simplest type of mathematical group. Here's another illustration. Add 2 even numbers, and you get an even number. Add an odd number and an even number, and you get an odd number. Add 2 odd numbers, and you get an even number again. Adding an even number is like doing nothing, since it doesn't change the status from even to odd. It's like dividing any whole number by 2. For even numbers, the remainder is 0. For odd numbers, it's 1. And this is also a simple mathematical group. Now, the 3 transformations, inversion, retrograde, and retrograde inversion, form a much more complicated group. It's a bit beyond our current course, but rest assured, the math has all been worked out, and it explains the musical transformations beautifully and completely. Bach's brilliance. Johann Sebastian Bach was a genius. He was a grand master of innovation of structure and invention in music. His 2-part and 3-part inventions are aptly named. What really adds to his genius status is that his compositions are rooted in fundamental mathematics. Bach played with symmetry and transformations. He composed fugues and canons that use multiple themes and voices that were developed by interweaving all the parts into a well-defined single structure. He experimented with turning music upside down and backwards, slowing it down and speeding it up. A wonderful example can be heard in his Art of the Fugue, Contrapunctus number 7. About 50 years ago, 1974, Bach's own first edition of his Goldberg Variations was discovered in a private collection in France. In it were 14 canons. The authenticity was established in part because 2 of the canons were known previously. Catalogued as BWV 1087, they are known as the 14 canons or the Goldberg canons. Bach tells us in his own handwriting that the canons are based on 8 bass notes, called a ground, from an aria in the Goldberg Variations. Each of the 14 canons uses transformations. They form a set of puzzles to be solved, with clues provided in unconventional musical notation. All are written compactly on a single sheet, comprising less than 10 minutes of music. The early ones are simpler and are stepping stones to later, more complicated ones. Canon 1 uses a retrograde transformation. The theme is heard twice, then the retrograde or backwards version, and then both together. Bach wrote it using only a single staff, but he put a second clef backwards at the end of the line to provide a clue about how to play the canon, which is as a duet, and it is a mathematical group. Canon 3 uses inversion. Bach assembled it as the original melody, the inverted melody to start 4 notes after the melody, and then a repetition of the sequence. Again, he wrote it only on a single staff, but the clue here is the placement of a sharp on a second clef, which only makes sense if the music is read upside down. Now, Canon 2 uses a retrograde inversion. It has the original melody, an inversion of the melody, and then the retrograde inversion. The inversion and the retrograde inversion are each played twice, and then both are played together. By the time we got to Canon 5, or he got to Canon 5, Bach introduced a new melody and its inversion. So now there are 2 bass lines. One is the main theme, the other is its inversion. If you're wondering, yes, this is a mathematical group too. Now, Canon 14, the last of them, is again written as a single line of music, accompanied by an instruction explaining it is to be played by 4 instruments, all at different speeds. That's the augmentation and diminution transformation. 2 of the 4 also need to play the line upside down, the inversion transformation. So here are the 4 parts. The top voice plays the music as written. The next voice plays at half speed plus inverted and transposed. The next voice plays at 1/4 speed and transposed again. And the bottom voice plays at 1/8 speed plus inverted and transposed. Remarkably, the bottom voice is the original melody from the Goldberg Variation. All the parts are, in some sense, the same, but they're transformed from the original melody. With brilliant cleverness, Bach figured out the basic underlying ideas of group theory about 100 years before that mathematical idea had been discovered. It is another prime example of Bach's genius. Martin Perlman comments that the 14 canons appear to be intellectual musings by one of the greatest musical minds in history. Bach's works provide other examples. Earlier, I mentioned Canon 1 of his musical offering as an example of a retrograde canon. The musical offering has other parts that show clever ways of playing with symmetry and transformation. So do the canonic variations on Vom Himmelhoch, BWV 769. Using mathematical transformations to compose a canon can make it more interesting, but that is no guarantee of a good sounding result. It worked well in the hands of J.S. Bach, but he was a genius at this. Something more than math is needed. I have a little coda. Bach's Art of the Fugue ends with an incomplete fugue. It is significant in many ways, including another little puzzle. The third subject begins with B flat, A, C, B natural. Using German notation for the notes on a scale, that is BACH. It is a signature stamp to conclude his life's work, and the only time in all his works that he used this autobiographical figure. I have a newfound respect and admiration for Johann Sebastian Bach. I, of course, knew about his musical genius. Now I know about his mathematical genius and his appreciation for puzzles. Bach excels at math, music, and puzzles. 3 of my great fascinations. I hesitate to call them passions because Bach wrote passions too. Finally, here is a nugget about Bach that I noticed. A score means 20 items. A score is also a transcript of a musical composition. Isn't it appropriate that Bach had 20, a score of children?